So I'll be talking about our AI data pipeline, specifically with TensorFlow and with PyTorch. So if you have checked out your GitHub repo that we've been using for this workshop, please do another pull. Just make sure you're up to date. And we'll be working down in the AI data pipelines section. I don't know if that's a microphone or air conditioner. So I'm going to start with the TensorFlow example. Both TensorFlow and PyTorch come with data APIs. I would say that the TensorFlow version is a little bit more robust and performant than the PyTorch. My guess is that's mostly because, or that's due mostly to the fact that people tend to write their own data APIs in PyTorch. And so they haven't felt the need to build that out. Okay, so we'll be using the ImageNet dataset as an example. ImageNet is just a bunch of JPEGs. Each JPEG comes with an XML file that has information about what's in the image. So it tells you the class of the object. Typically, every image is a single object, like in this case, a turtle or a dog, and you'll get a bounding box that tells you the specific box that goes around the object that's being labeled. And that's so you can do different types of classifiers, right? And so we're going to build a data set or a data pipeline that uses the bounding box to extract the single object, and each batch of our data will be one object based on the bounding box. So we won't be doing something like YOLO. We'll be doing something simple like ImageNet. And so let's go over here. So if you've checked out our repository, which I have here, and then I'm down in the AI data pipelines. That's probably not readable. Let's go over here. SSH into Polaris. And then I can make this a little bigger so that it's easier to see. So then I will go to and AI data pipelines, and then we'll start in the TensorFlow dataset API. Okay, so that's where I'm going to be over here. Let me see if I can make this a little bigger. Okay. And if we go to the TensorFlow dataset API, and then I open the Python code that's there, and make this full screen. And let's just go through this. So in this example, I'm using TensorFlow, and I'm also using some built-in Python XML parsing. And the idea here is that I have this dataset, get datasets function, which is going to be passed a JSON configuration with some information about our images, and then it will build our training and our data validation data set out of those config files. And if I open that config file, which is here, you're going to see that I specify different things. So for instance, the batch size gets specified here. And then I also have a file list of all the images. So if I were to open this file, we're going to open that anyway because it's really big. What you'll find in that file is that it's just an individual, it's a list of all the images that are in the data set on our file system here. Hopefully, these are all readable because they're down in our datasets project, which should be open to everyone. But you see here, there's a JPEG, and we could go there and list this JPEG and have a look at it if we wanted to. and see the images. Each of these files has a corresponding XML file with the metadata about it. We can go look at that real quick just so you can get an idea of what kind of data you're dealing with. I think I have to go to annotations. And yes. And I'm just going to pick an example here. So this is all XML format. And what you're going to find is, the base name. This identifier identifies the class, like it's a UID for the class object. The ImageNet dataset contains 1,000 different image or object class identifiers. I don't know why they gave it this ridiculous number instead of naming it 0 to 1,000, but we will do that in our processing example. And then it provides a bounding box. Like I said, typically in this ImageNet dataset, there's one class of object per image. So you might have a picture of a turtle, or there might be 3 turtles in your picture. So all the bounding boxes would organize around those, would give you each individual turtle, but they're all the same class. Okay. So now we will go to, we're going to get our Python back up here. There we go. Okay, so the config file tells the software where to find that file list. It's separated into 2, one for training, one for validation. And there's other things in here that we'll talk about as we go through. And the idea here is to use everything that TensorFlow provides in our dataset API creation. And the benefit of doing that is that TensorFlow does a lot of optimization on the background. So as we build out this dataset API, this pipeline, we're going to be calling TensorFlow functions, and those functions won't immediately operate on our data, right? We're just telling it, here are the instructions for processing our data. So we're going to give it that workflow. Then in our training loop, we're going to say, give me a batch. And that's when it implements our dataset API, okay? And that's important to understand because you're not going to see during the initialization and the creation or the execution of this Python code that there's going to be any data processing going on. So let's start with, this is the high level function here, build a data set from the file list. So I'm going to pass in my file list and the configuration. And so that brings us down here. I'm also keeping track, in this example, I'm using Horovot for any sort of parallel data training. So it's keeping track of whether or not this is, what rank this is. So I'm going to grab my configuration, checking how many ranks I have, opening up that file list, reading all of those strings into a Python list. So this is actually happening in real time, but it's very quick because that file list is, 80 megs. And so now we're going to, this is just a quick printout for the user to see how many batches we'll effectively have. It's an estimation based on the number of images, but obviously will be slightly different. This is just so I can kind of keep track of how long this is going to run. So the first piece of our API is really this step here, where we take the Python list of file strings, the paths for each file that has our image in it, and we create a tensor based on that list. So we say, here, TensorFlow, create a data set based on these strings. It's just going to be a list of strings at this point. This is some dealing with some parallelism. We're just telling it how many threads to use, and I'm going to base that on this environment variable from OpenMP that sets the number of threads for any thread pools that it decides to instantiate. Okay? And then I'm going to say, okay, I want that to be part of my dataset API. So this is a configuration for the dataset. Now, if I'm using Horovot, which means I've got MPI in the mix, I want to make sure that every rank isn't processing the exact same data. I want to shard the data over the MPI ranks. Sharding is the term they use. It really just means, in this case, I have a list of files that are each individual data. One rank is going to process, the first rank will process the first 10. The next one will do the next one, and so on and so forth. And it's going to handle that for me. I just have to tell it how many ranks I'm going to have. So the total number of MPI ranks, and which rank am I? And it's just going to do the indexing there for you. The next I'm going to tell it I do want to shuffle. So anytime there's an epoch boundary, or I've iterated over all of the data in my data set, I want TensorFlow to shuffle all the images into a different random order so that I can make sure I'm doing a robust training and not just learning how to train on sets. And you notice that each of these, essentially what I'm doing is I'm calling the data set with a function, and it's returning a new data set object that's been modified, essentially. So each time I'm doing this, I'm overriding the old one, essentially. And on the back end, TensorFlow is building out a graph of each of these steps that it's going to do. The next is I'm going to run this custom Python function that I wrote, where for each input image, it's going to process multiple files in parallel, and it's going to open the JPEG, it's going to convert it to a TensorFlow tensor, and then it's going to get the truth label for that object in the image. And we'll look at that. But the point here is that this is a mapping call, and I can tell it how many of these can it run in parallel. And this is, again, a place where I'm optimizing the execution. Keep in mind my data set, and I should have said this at the beginning, the goal of your data API typically is to be running in parallel to your training and not blocking the training, right? You've got a GPU sitting here, you've got a CPU sitting here. I'm going to run my data API on the CPU, and I'm going to be feeding the GPU with training data. And it's just going to be training and training. And in the ideal case, the execution time here is equivalent. So the amount of time I spend training, by the time I'm done training on that data set, I already have the next batch ready to go. Okay? So this is a parallel workflow between the two pieces of hardware. Obviously, you can have more complicated setups. Training an LLM is much more complicated, right? So this would be, and plus I would also point out that the way I'm doing this one here is very stupid. And we'll see that when we start looking at the profiles. Because you wouldn't want to be opening a single image every time you need to look at it, right? You would want these already stored in large chunks of tensors, pre-processed, however you need them done, before you start your training loop, okay? But this is just to give you that run through of how you can build up an effective data flow on the CPU while you're doing your training on the GPU in parallel. So let's take a look at this, this function real quick. So this is being passed the image path that we created initially. So it's the first thing that starts processing the actual data set. And what you'll see here is we're going to parse these, this image path, and I need to be able to know where the XML file is so that I can extract the bounding box and the image class. And what you see here is I'm doing that all with TensorFlow operations. So I'm replacing pieces of the image path from data to annotations and from JPEG to XML. Those are the transformations on the string that give me the XML file path, okay? So those are all done with TensorFlow operations, which allows me, those are becoming part of the graph, right? Those are part of the graph that's going to be executed, and TensorFlow knows how to optimize those and do those in smart ways. Next, I'm going to run a Python function that I wrote that extracts those bounding boxes from the annotation file. But I wrap it in this Py function call to let TensorFlow know that this doesn't use TensorFlow operations, so it's going to have to do some special processing to optimize it, okay? So we're going to go take a look down here real quick. It's not that big a deal. It's opening up the file for the XML file using the standard Python XML parsing library to extract these xmin, the ymin, xmin, xy max, and returning those as a NumPy array. And so in principle, at this stage, we now, of our dataset API, we now have our bounding boxes and how many there are. Now we continue with the TensorFlow dataset pipeline, using the TensorFlow operators. Now we're going to actually open up our image file. This is going to process it into Torch or into TensorFlow tensors. We're going to decode it from its image. This is some sort of byte data, byte string data. It's going to convert it into the actual RGB plus channels that we're accustomed to in images. And then we're going to add a batching dimension in the front. So this expand dimensions just adds this in the front, because what was recovered from the decode JPEG was only the image data. But we need to be able to batch these together, so we needed an additional index on our array. Now we want to crop and resize our image data based on our bounding boxes. And TensorFlow includes a very nice function that already does this. I just have to pass it the bounding boxes, the indices, the original image, and how big I want the output size to be. Because instead of having every bounding box being some custom size, my model requires a fixed input, right? So if I'm doing some simple image classifier, I can't have variable size images that I'm passing into that model. They all need to be the same size. And that's where I set that to just be a standard 256 by 256. These are square images. It will do some scaling to bring that back. Or no, actually, no, I have a resize step down here. I'm not sure what that is doing there, actually. Maybe doing this duplicated, so that extra step might not need to be there. Anyway, here I'm converting the data type. If you wanted to add in some change in the data size, you can do that. You can add that to your data pipeline. Here's some resizing of the images. So you'll notice at this stage, I have renamed this to images because this is now multiple images based on the bounding boxes. If I have more than one bounding box, I could have more than one images here. I'm going to convert the data type, resize those. I'm going to look up the label. So I created this label hash that just takes those unique IDs. It skims over the file list, grabs the unique IDs from the file names, and creates a hash from 0 to 999 that maps those. And so I need to find out which label am I based on the file name, and create multiple labels if there's multiple images. And now my data set ends with returning the batch of images, or returns the images and the labels for this single file, right? So this is processing one image, okay? So now we go back to where we called that, right here. So the nice thing is these can be happening in parallel. So I can have parallel reads of images going on, and those are being passed to the next step. This is an unbatching step. This is required because some of my JPEGs have one class object inside. Some images have multiple. So when this data comes back, it's coming back with each of those files, the input files, have been converted to any number of images and labels, and we don't know what that is. So what this unbatch operation does is it flattens everything. So now I just have a big long list of images and labels, one per entry, and now I rebatch it however I decided in my config file, which I think was 128, yeah. 128 batch size. I can batch in parallel as well. So there are actually 3 levels of parallelization, but let's focus on 2. So the first one that we covered was reading in our images in separate threads. So it can do that. The next one is creating batches. So imagine you have a queue of all the images that have already been read and processed by your reading threads, and they just place their outputs on a queue somewhere. And then you have another thread or more, which are creating batches for your training loop. And so they're grabbing stuff off the queue, building a tensor of n images based on your batch size, and then passing those to the training loop, okay? So we have those 2 levels. TensorFlow also can do interoperational parallelization. So anytime you do math ops in your data pipeline, it sometimes has internal OpenMP implementations of those. So if you're manipulating your images, if you're doing math on your data, it can vectorize those for you. It can parallelize those for you based on its internal implementation for the device, like a CUDA device or an AMD that you might be running on. And then the last thing I'm going to add to my pipeline here is a prefetch call. Prefetch just means that my threads that are creating batches are allowed to go to the next batch if they're done. And that just means that you can have a couple of batches waiting in line for your training loop. And so that's another layer of making sure that your CPU is always busy while your GPU is busy. Okay. So that's just to get to this dataset object, which was returned back here. So I'm going to do that twice, one for a training dataset, one for validation. And then we're going to go back to, we're going to actually look at the main loop now. So if you look at our main loop, you can see I'm grabbing GPU information, reporting that out, grabbing my configuration, handling some parallelization here with TensorFlow. And I also have the TensorFlow profiler implemented here if we care to do that. And then I make this call to the get datasets. And so now I have these dataset objects, and I can start my dataset pipeline. Now, in principle, if I didn't want the profiling going on, I would just do something like if I were in the epoch, that's fine. Okay, that's epoch. But once I'm in the training loop, I could just say images labels on train dataset. And so you can iterate over data sets, and that's fine. I don't do that in this example because I'm going to show you TensorFlow, its built-in profiler, and to capture the, when I do 4 image labels in the training data set, this call here is what's going to tell TensorFlow, now go do the data flow. Now go do it. And it's going to implement that. So I wanted to trace that inside the profiler, so I do it by hand. So in case you're, and you're like, this looks way too convoluted. It's only convoluted because I'm trying to profile so that you guys can see the performance differences. So this really just loops over some number of steps. For each time that we call the training data set for images and labels, it's going to keep track of that for us, and it's going to label this with the training step. And I think the training step count is set on the command line. Yeah, defaults to 10. So we'll do 10 steps. We're going to time it and print out some number of images per second that we've processed. So kind of a performance metric. And then we'll see how that works. I'm going to revert this file because it was edited. Okay, so then we're ready to run. Are there any questions at this point?
I think I missed what you said. Pipeline, which is sourcing the data. So you said something about you have multiple class data files, you're able to pick out the different classes of objects from it. So if it happens before the training, happens when you're just sourcing the files?
So the data flow will happen during the training loop. Like if this was a training loop, right, what you would see here is after I get my inputs and my labels, I'm going to add, train model code goes here, right? So this would be, outputs equals model inputs. Now I haven't created a model here, so there's nothing to train, but that's how your workflow would go. And the point is that with every iteration of this loop, you're calling the dataset API saying, hey, give me more data to train. And that API is running in parallel in the background outside of this thread, right? This is running in your main thread, your main process, and TensorFlow, based on your creation of your data API, has now spawned a bunch of parallel threads that are in the background, reading images, packing them into batches, getting them ready for this thread to say, okay, I'm ready for my next set. Okay? Does that make sense? Okay, so now we can go over here. You guys can submit. I put in a submission script in here. We'll take a look at it real quick. This is just setting up Python using our Conda environment. Hopefully you've seen that by now. I set the number of nodes, number of GPUs per node, so I can calculate the number of ranks. And then I'm going to run this for a different set of parallels operations on my CPU. So for the first example, we're going to say only use one thread. This terrible performance, just use one thread, and we want to see how bad it is, right? So this gives us as an example of what our performance would be like if we didn't have the parallelization. And so then I launch my 4 ranks on a single node, and I'm setting my CPU depth to MPI, passing the OpenMP environment variables, and then I'm launching the Python with the config. I'm setting TensorFlow parallelization here. If there are questions about this, happy to talk after the talk, but I don't want to focus on this. This is really just configuration code that TensorFlow uses for defining the different levels of parallelization that they offer. And then I'm telling it to dump all of the log information into the log directory so that it doesn't muck up the working directory that we're in. Then I do it for 16 and 64 threads, okay? So you can, Q sub that on the command line. I think the project here is ALCF training, and then we've got a special queue. You guys use that. I'm just going to use this one for quick turnaround. Okay, so I already have some results that we can look at, but this will run. It's going to spit out some files into this log directory. So you're going to get your, what you should see in the log directory are the actual execution, logging that goes here. You'll see the images per second. And you'll see how that changes with the number of threads. So we started in the 100 images per second. Adding 16 threads gets us up to 1,400 images per second. And going to 64 threads gets us up to 2,800 images per second, okay? So threading really gives us a big boost in our performance, right? I mean, that's almost 2,900 divided by 125, so right, factor of 20. My guess is this hasn't run during the day. The debug queue gets a little busy, but you guys should have this go through pretty quickly if you're using the reservation. Okay, so you get that, but then there's going to be this plugins, and these are where the TensorFlow TensorBoard profiling output goes. TensorBoard has a web API that you can use that's really nice. And the way I typically use it is I will log into Polaris, and I have the instructions in the readmes here, so no worries if I'm going too quick. What I usually do is I SSH and I do a port forward. I'm going to select 9999. Now that I've selected that, you can't use it. Can't all use the same ports on the same machine. So randomly choose your own 4-digit port number. I think it has to be, I think 4 digits is safe everywhere. Is that right? As long as it's above 1,000. There is somewhere that there are reserved ports, but anyway. Okay, so now I have that port set up. I'm going to module load conda, activate that. I'm going to go down into my repository where we're working, into the AI data pipelines, into the TensorFlow example. Now I'm going to start TensorBoard. So TensorBoard, yeah. So I'm going to start TensorBoard. I'm going to set a log directory for that, which just happens to be named log directory in my example. I'm going to set this bind all. That just means go off and find everything in these subdirectories and make sure you load them. And this is the default port, but I set it anyway. If you're on the same machine, you might have to set that differently. If you don't set the port and the default one is taken, TensorBoard will grab the next available above. It just increments until it successfully binds to a port. This will start up. And it should end with a report of where you can find. And the main thing here is to check that it got which port did it assign, okay? So here we can see I got the 6006. So you remember that I set up the port forwarding when I logged in. I did that SSH-D9999. I'm going to open up Firefox. I find it easier to deal with proxies in Firefox than Chrome because Chrome just uses the system settings. Firefox, you can open up the settings, go to the network settings, and set it to a manual proxy configuration, a SOX host of localhost, and then I'm going to set it to that number that I used when I SSH'd. So now it's going to use that port to access the web. Setting to SOX 5, I think that's set by default anyway. And now you should be able to type in localhost and then the port number that TensorFlow or TensorBoard is using, so this 6006. And if you enter that in, hopefully, you'll see the TensorBoard interface. So now I'm routing all of my web traffic through the login node of Polaris, and I'm accessing that web server that's running there. And what you'll see are the runs that are down in your log directory. Now, we run three tests very quickly in the same job. They'll typically get a timestamp, not like this one was the 1 thread job, and this one was the 16 and the 64. So you just look for the time that's near where your run was and the order of the timestamps. So you see this is year, month, day, hour, minute, second. So I'm going to look at these 1031s. I ran this morning, and I'm going to grab the earliest time. Is it 1534? I think so. Yep. Okay. So this is the 1 thread case. And when I go down to, so I mean, there's a lot of information in here for you to unpack. I always find the most useful information is the trace viewer. The trace viewer is going to give you a rundown of what all your threads were doing in TensorFlow operations. Okay? And you'll remember, and if you don't, let's just take a look. When I did this trace with the profiler, I gave it a name, and I named it based on the steps, the iterators. And so what you'll see, if I zoom in, and we look in here, what you'll see is that train step 03. So this is train step number 3, this train step number 4. And each of these sections, here's the GPU. We're not doing any training here. So all we're going to see there is the TensorFlow is trying to handle the memory copy for us. So TensorFlow knows that I requested GPUs, and it's going to copy that data to the GPU. Okay? So here you see the mem copies to and from the host and the device. Nothing else. But if you were running a model, the really nice thing is you would also see where your model training was falling. And if you've got big gaps between your model training and your CPU is busy the whole time, you know that your data flow is holding up your training. If you could shrink the time on the CPU, get your batches to the GPU faster, then it would be better, right? And that's where I say this workflow is stupid, because I'm opening up these tiny little JPEGs every time I want to read them, which is just a bad idea, but it's to prove a point. So now we go down into our parallel threads. Now you can see, even though I told TensorFlow only use 1 thread, it's still a bit greedy, and it's already got, the main Python, and then it's got a couple of threads going on down here. But what you can see, if I zoom in down here, you can see the parallel batch structure coming into view. You can see, here's this eager pi function. And that is literally, where is it? That is this being called. So that's our bounding box, which is also doing a read, right? Because we're reading in that XML file. So you can very quickly see that I'm bounded here by reading data from the file system, which makes sense, right? I'm doing a bunch of small reads from the shared file system, which has been optimized for reading large amounts of data all at once. Okay, so we can see the execution of our data pipeline, right? Here's the decode JPEG, right? And we've got some resizes going on here, the cast for the data type going on. So you can see all those pieces of our data flow being executed. Even inside of our custom Python, we can see where TensorFlow has done some optimization for us on that, even though we wrote that code with different, with just vanilla Python. So now let's go to the next run, which is 16 threads. Each row is a different thread. I forgot to highlight that at the top of this is runtime, starting with, oh, darn it. Let's go back here real quick, because I want you to see, there we go. So you can see the runtime at the top here, and you can see we are, over 40 seconds, probably at about 50 seconds in runtime total for this job. with a serial-like workflow. So once I go to 16 parallel threads, you can see now I'm down below 6 seconds. So now I'm running much faster, getting through those 10 steps. Okay, so now we can see down here there are quite a few more threads being executed. Right, and they're all doing various things. Some of these, right, you can see the parallel batching going on. And then you can really see that all of this other stuff is dominated by the green and the brown, which is the read file, the JPEG, and the read XML file in the Python function that we made, okay? So you can see that, but the nice thing is we've gained time because these things are all happening in parallel now instead of just one at a time. And at some point I did do this with a model, and you could see that by the time we get to 64 threads, so in this case, this just keeps going. Like as soon as it gets a batch, it goes for the next one. So it never maxes out the workflow. And here you can see we're now, under 5 seconds runtime. And we're really now, most of our execution time is in all of this pre-setup. And of course, our first training step takes the longest because it's instantiating all the data flow. That's the first time our request for data has been made. And so you can see our data, there's like some building of the workflow, there's probably some compilation happening here. And then eventually the data flow starts up. So again, we get lots of threads now. You can count these all up and you would find 64 of them. And we can down into, whoops, that's not the zoom I want this zoom. There we go. You can dig down in here and you can see all of our IO taking up all the time. So, if you saw this during debugging, oh, well, clearly I shouldn't be reading all of these files all the time. So you would go through and make a separate Python executable that would read in all these JPEGs, shove them into HDF5 files or TF records, and you would have you would read in big chunks of images all at once, thousands of images in one file with gigabyte sizes instead of, a kilobyte JPEG. And that would be how you would optimize your data workflow in this case. And then probably the last thing to point out is you can do a similar thing in TensorFlow. And so I have that in here as an example. But the PyTorch data API does not parallelize as well as the TensorFlow one does. So you may very well find that your own implementation works better. With the equivalent PyTorch implementation, I was able to get something like 600 or 700 images per second max. And I think that's because I could never convince the API to do the file opening in parallel. The API is built around, for an iteratable data set, you build one batch per thread. So you would either have to implement your own version of parallelization at the image level or build your own API, which I think is probably what most people are doing that are using PyTorch. So any questions about those?
Wow, very informative. With no questions, I guess. Everything was covered. Are we sure nobody has any questions for Taylor about the
No,
content?
no, you don't have to invent questions. It's okay.
All right, so I guess let's thank Taylor.